Hi, welcome back. This is Professor Ridge and today's lesson on section 9.1, composites and inverse functions. So the composite function, f composed with g, is defined as, so the way you read that little, it's like a degree mark almost. A lot of people say fog, but it's f composed with g of x is f of g of x. So basically what you do, so if you recall, g of x, this is a y value for the function g given x. So you're going to plug x into g, get a y value, then you're going to take that answer and plug it into f. So you take x, plug it into g, get a value, a function value, and then you're going to take that value and plug it into f. So basically, we can kind of think of it this way. If we work inside out, so g is this box, we plug in x, it spits out a y value, g of x, and then you're going to take that number, plug it into the f function, and it's going to spit out f of g of x. Okay, so that's the composite function. So let's look at an example, or let's do an exercise. Hang on. Okay, so we want to find f composed with g of 1, g composed with f of 1, f composed with g of x, and g composed with f of x. So all four of those things. So f composed with g of 1, we're going to apply the definition that I wrote up here. The composition of functions. So it's going to be f of g of 1. So our first step is figure out what g of 1 is. So remember, the g function is x squared minus 5, but we don't want x, we want 1. So you put 1 in there. 1 squared minus 5. 1 squared minus 5 is 1 minus 5, which is negative 4. So g of 1 is negative 4, and now I'm going to do f of negative 4, so I put the negative 4 into the f function. The f function is x. You're going to take whatever you plug in and add 4 to it. So I'm going to put negative 4 in for x. So my final answer would be 0 for A. For B, I'm going to switch it around. G composed with f of 1. By definition, it's g of f of 1. We're going to plug the 1 into the f function first. So the f function is, you're going to take x, which in this case is going to be 1, and add 4 to it. So that's going to get us 5. 1 plus 4 is 5. Now we're going to plug the 5 into the g function. The g function is, we take x squared minus 5. So x in this case is 5. 25 minus 5 is 20. So g composed with f of 1 is 20. Alright, now we want to do, that was B. Now we want to do f composed with g of x. Well, by definition, that's f of g of x. Well, g of x is x squared minus 5. And then f is x plus 4, but we're going to put in x squared minus 5. And just simplify it. X squared minus 5 plus 4 is x squared minus 1. And you can check A. If we were to plug in 1 squared minus 1 is 0. And then B, we're going to do it the other way around. G composed with f of x. Apply the definition, g of f of x. So g is x plus 4. I'm sorry, f of x is x plus 4. And then g is x squared minus 5. Now notice I just put a parenthesis and I didn't write x. Now whatever I put inside the parenthesis, I got to put in this parenthesis. So wherever I see the x, I put just a blank parenthesis there. And then whatever I plug in this parenthesis, I have to replace the parenthesis with what's inside, x plus 4. Now, do some algebra to simplify that. X plus 4 times x plus 4. Hopefully by now you got this down. X squared plus 8x plus 16, which is x squared plus 8x minus plus 11. So that's composition of functions. Okay, so on number 22, they want you to break the function up into two functions, f and g, such that h of x is the composition of f composed with g of x. Okay, so the way I think of it is, if you can, g of x is the inside one. So if we applied this definition, we're going to get f of, remember, you're going to get f of g of x. So think of it as an inside function and an outside function. So here, in the parentheses, if you let the inside function be what's inside the parentheses, so we're going to let g of x be, and there's more than one right answer for these, by the way. But the easiest way I would do it is think of it as an inside function and an outside function. So we're going to let the inside function, which is the g of x in this case, be what's inside the parentheses. So 2x plus 7. And then now just if you were to kind of wipe that 2x plus 7 away and just put an x there, you'd see the outside function would be cubed. So we're going to let f of x be just the cubing. So f of x would be x cubed. And if you compose those two functions, you'll get h of x. Okay, so that's kind of the easiest way to kind of view that. So think of it as an inside function and an outside function. Another way you could think of it is if you thought of it as order operations and you looked at all the steps and just kind of draw a line somewhere to split it up into two functions. That'd be another way to do it. Alright, so let's try the next technique. So a function is one-to-one, so new term here, if different inputs have different outputs. So that is, if for a and b in the domain of f with a not equal to b, so if you have two different input values, remember domain's input, then those input values give you different output values, y. So basically, and then so that means it's one-to-one. So basically, you can think of it for each x, there's only one y. For each x value, there's only one y value. That's the function part. And for each y, there's only one x. That makes it one-to-one. Okay, so to be a one-to-one function, it has to be a function. So for every x, there's only one y. And to be one-to-one, for every y, there's only one x. Okay, so if you remember when we did functions, if you had 1, 2, 3, 4, and say 3, 5, this would be a function. So that's a function. But it's not one-to-one. Here we can write one-to-one like that. Okay, so to be one-to-one function would have to be like if we had 1, 2, 3, 4, each of these can only go, they have to go to different y values. So maybe like 7, 8, 9, 10. Domain range. Okay, domain range. So the each x value getting one y value, that's the function part, and then each y has a different x, then that's one-to-one. One-to-one function. Okay, another way, if you recall too, we had what was called the horizontal line test, the vertical line test for function. So each vertical line is testing an x value to see if you only have one y value. So if we had something like this, that would pass the vertical line test to be a function. So it passes. So it's a function. Now to test one-to-one, you do a horizontal line test. Look, here's a horizontal line. This is a y value. It has two x values. So it's not one-to-one. Okay, so it's a function because it passes the vertical line test, but it's not a one-to-one function because then you do what's called the horizontal line test. Okay, so horizontal line test. And it's just like a vertical line test, but now you're testing y values. And that's for one-to-one. So to be a one-to-one function, it has to pass both the horizontal line test and the vertical line test. So if you know it's a function, there's no need to do the vertical line test, but if you want to know if it's a one-to-one function, then you do the horizontal line test. Okay? So I can ask you a question, is this a one-to-one function, and just draw a picture. So let me draw some pictures. Okay, so the following one-to-one functions. So again, they have to pass both the vertical line test and the horizontal line test. So A is one-to-one. B, no, because it fails the vertical line test, so it's not even a function. It passes horizontal line test, but it has to pass both, remember? C is neither one, so this is definitely not. And then the last one passes both functions, right? Vertical line test, fine, so it's a function. Horizontal line test, yep. So yes. So A and B are one-to-one functions. And B and C are not functions at all. So let me do one more. What would be a function that's not one-to-one? Well, it'd be that one that I drew up there, like a parabola, or even if I had something like this. And that's not one-to-one because here's a horizontal line that has 3x values. So no. But it is a function. Okay? So you can be a function and not a one-to-one function. So a one-to-one function is very selective. Now, one theorem about a one-to-one function, it has what's called an inverse, and an inverse is basically you just switch it has an inverse function. Inverse, you just switch the x and y's. So inverse correspondence is just switching the input values and the output values. So an example would be if, say, 3, 8 is in your function f, then the inverse function would be 8, 3. So you just switch it around. Okay, so if you have x, y, then the inverse would be y, x. So you just switch all your x values with all your y values. Okay, so if we had f is equal to 1, 2, 3, 4, 7, 12. And here's the way you do the notation. F inverse, this is the inverse of S, would be, and you just switch all the x and y coordinates. So 2, 1, 4, 3. So it's the way you go backwards. Get back to where you started. So like if I said take 5 steps forward, the inverse of that would be take 5 steps back. All right. Now, to be an inverse function, if a function is one-to-one, if a function is one-to-one, then its inverse correspondence is also a function. So if it's not a one-to-one function, the inverse of it wouldn't be a function. But so it has to be a one-to-one function for the inverse to be a function. Okay, so find the inverse function. So let's say g of x is that. So our first step is you're going to write y for your function notation. So in this case, we're going to write y equals 2x minus 3. Then because to do the inverse, right, like we did up there, 1, 2, and then you switch it to 1. If it's xy, you switch it to yx. So we're going to switch the x and y. And none of the numbers, just the actual x becomes a y and the y becomes an x. But you leave all the numbers and the coefficients the same. So this is going to become x equals 2y minus 3. Okay? And your next step is you're going to solve it for y. Get y out by itself. So just do some normal algebra. So you got x plus 3 equals 2y. Divide both sides by 2. So we got y equals x plus 3 over 2. And then your last step is now you're going to write the y as the function inverse. Using the -1. Notation. Now that's not a -1 exponent even though it looks like it. So this was g. So g inverse of x is going to be x plus 3 over 2. Now again, that's not a -1 power. It's just the notation g inverse, which can be confusing sometimes. You got to keep it straight. All right, let's try 54. Same question. So we're going to make the y. Now we're going to switch the x and y. So that'll be x equals y cubed minus 4. Add 4 to both sides. So x plus 4 equals y cubed. Now we're going to take x plus 4 equals y cubed. Cube root both sides. So cube root of x plus 4 equals y. So f inverse of x is equal to the cube root of x plus 4. Okay, so graph each function and its inverse on the same set of axes. So again, we can use slope-intercept form. Y, we're going to start at y equals 2, and then the slope's up 1 over 4. Now notice this is 0, 2, this is 4, 3. Now remember the inverse is you're going to switch the x and y. So if this is 0, 2, the inverse is going to be 2, 0. So we plot 2, 0. Well, first that was a line, so I can draw the line through it. 1, let's go -4. This is y equal, this is g of x. Now if I want to do y equals g inverse of x, I just switched those points around. So let's see, this was negative 4, 1. So, and then this was 4, 3. So if I have 4, 3, I switch around 3, 4. Oh, and one other thing too. Since you're switching around the line y equals x, if we draw this line right here, y equals x, y equals x, it's a mirror image through that line. So you see this point crosses there. We got 4, 3. This is going to be 3, 4. And it's a mirror image. And then this point was, let's see, 4, 3, 3, 4, negative 4, 1. So I want 1, negative 4 right here. And you can see that I'm crossing this line is my y is g inverse. Now I don't really need to know what I don't have to actually work it out because I can just switch it around. It's the reflection through this dotted line I drew in the middle here. Okay? Now if I wanted to work it out and graph it, you certainly can do that. So we know that y equals 1/4 x plus 2. We switch the x and y. Solve it, so subtract 2, and then multiply everything by 4. So my g inverse of x is 4x minus 8. And you can definitely see that if this would be way down here at negative 8, 5, 6, 7, 8. Down here's where it crosses. And then you're going to go up 4 over 1. Up 4 over 1. So then you get the same point. So you can, it's up to you. You can figure out what this equation is and graph it, or you can do what I just did. You graph the one line and you just take all the x values and x and y values and you switch them. And it's the reflection through this line y equals x, because you're switching. X becomes y, y becomes x. Okay, so that's up to you. Do it either of those two ways. And let's see, one last thing. Composition. If f and g are inverse functions of each other, then f composed with g is going to be equal to x. And then you can switch it around. G composed with f of x is going to be equal to x. Okay? So another way of saying the same thing, if f composed with f inverse, that's x, and f inverse composed with f. So since inverse functions, basically they cancel each other out, right? If ones take 5 steps forward, the other ones take 5 steps back, where are you going to end up? Where if you start at x, you're going to end up at x. So that's the idea. Okay, so, and that's also the check to see if two functions are inverse. So number 70, it says show that if f of x equals cube root of x minus 4, oh, this is number 69, sorry. Show that f inverse is x cubed plus 4. So what you got to do is you start out with f composed with f inverse of x, which is f of f inverse of x, and see if you end up at x. So we put in the f inverse, which is, we're claiming it to be x cubed plus 4, and we're going to plug that into f, which is cube root of x minus 4, which is going to give me cube root of x. Okay, so I dropped the parentheses, the x plus x cubed plus 4 minus 4 cancel each other out. So that's cube root of x cubed, which is just x. Now you got to do it the other way around. So f inverse compose, you got to check both directions. It's pretty rare that it works for one but not the other one, but there are some oddball cases. Usually has to do with one-to-one, where if it works one way but it doesn't work the other way. So you have to check both just to see if it works. So let's see, we're going to do f inverse of f of x. f of x is the cube root of x minus 4. Plug that in the inverse, which is cube plus 4. Cube root of x minus 4. So the cube and cube root cancel each other. We get x minus 4 plus 4, which is just x. And that's the end of that proof. So that's, you know, an algebraic proof. You know, you write down the definition, you plug in the functions, you do the algebra to simplify it and see if you end up with what you're supposed to, which in this case we're supposed to get just x. And you got to do it both directions, which we did. And we see that we ended up at x, so f inverse is in fact what we claim it to be. Okay, so that completes the exercise, the lesson for 9.1. Go to my math lab and complete your exercises there. I'll see you next time.